Welcome to this Reigate College Maths Year 2 Further Maths Core Pure video on Maclaurin Series. So Maclaurin Series are where we write a function as a series of powers of x, and the formula for Maclaurin Series looks like this. For a general Maclaurin series. So it's f of x is equal to the function at its value of 0, f of 0, plus x times the derivative at x equals 0, plus f double dashed of 0 over 2 factorial times x squared, and so on. Here's the general term, the rth derivative of f evaluated at 0 divided by r factorial times x to the power of r. Now this formula is in your formula book. We're not going to go through the derivation of it, but there is a derivation or a proof of that formula in the textbook. It's example 7 on page 40, and I think, you know, if you have time, it is valuable to look at that. So what we're going to do is we're going to look at using that to derive the Maclaurin series for specific functions. So in question 1 here, the function that we're interested in is f of x is equal to ln of 1 plus x. So what we need to do this is, first of all, we need to differentiate f of x equals ln of 1 plus x. And we actually need to go up to the 5th derivative because we're going to need the x to the power of 5 term. We actually did that in the previous video. We looked at the derivatives of this function, so I'm just going to write them back out, and then we're going to look at their values at x equals 0. So for part A, f of x is equal to ln of 1 plus x. F dashed of x is equal to, actually no, this is slightly different, isn't it? Well, we'll go through it. So that's 1 plus x to the minus 1. It's 1 over 1 plus x, so we're going to write this as 1 plus x to the minus 1. F double dashed of x is equal to minus 1 plus x to the minus 2. Use the chain rule, differentiate the inside, you just get 1 anyway. F triple dashed of x is 2 times 1 plus x minus 3. Third derivative, which we use, sorry, that was the third derivative. Fourth derivative, we can write 4 there. We quite often put that in brackets. Of x is going to be minus 6, 1 plus x to the minus 4, and the 5th derivative is going to be 24 times 1 plus x to the minus 5. For our formula, we need those all evaluated at x equals 0. So we're going to say f of 0 is equal to ln of 1 plus 0, ln of 1, which is 0. F dashed of 0 is, put 0 in there, we're going to get 1. F double dashed of 0 is going to be minus 1. F triple dashed of 0 is going to be 2. F 4 at 0 is going to be minus 6, and f5 of 0 is equal to 24. So we need to use the formula, and we need to go up to the x to the power of 5 term. We're going to say, so f of x is equal to, well, the first term is f of 0, so we want 0 plus the second term is f dashed of 0 times x, so that's 1 times x. Third term is f double dashed of 0 divided by 2 factorial, so that's minus 1 over 2 x squared. And then plus 2 over 3 factorial x cubed minus 6 comes from there over 4 factorial x to the power of 4 plus 24 over 5 factorial x to the power of 5. And it's an infinite series, so it goes on forever. Let's just simplify those. So that's equal to x minus a half x squared plus a third x cubed. So this is 2 over 3 factorial is 6. A third x cubed minus 6 over 4 factorial is 24. So that's minus a quarter x to the power of 5 plus 5 factorial is 120, so this is a fifth x to the, oh sorry, that should have been to the power of 4, x to the power of 5. So there's our expansion up to x to the power of 5. So part B here says using only the first 3 terms of the series, so this one, this one, this one, find estimates for learn of 1.05, learn of 1.25, and learn of 1.8. So the values of x that we want to substitute in are 0.5, 0.25, and 1.8. So let's do that, and then in a moment we'll just see how these approximations look compared to the function itself. We'll have a look on Desmos. So learn of 1.05 is equal to 0.05 minus a half 0.05 squared plus a third of 0.05 cubed. And if you put that into your calculator, you get 1171 over 24000, or 0.0487917. So I've gone to 7 decimal places there, 6, or I think it was 6 significant figures. Learn of 1.25 is equal to, I'm not going to write out the all the working here, so you would put in 0.25, put in 0.25 squared here, and so on. This is 0.2239583, and learn of 1.8 is 0.6506667. What I do just want to show you is a quick way, relatively quick way to do that on the calculator. So what we can do is we can go menu and go down to table and select that. We can define our function. So we want our function to be the first 3 terms of that Maclaurin series expansion. So we're going to go x minus a half x x squared plus third x cubed. We're not going to define our function g, but then we're going to put into this table the values of x that we're interested in. So that is 0.05. We want it to go up to 0.8, and the step needs to be 0.05 as well. And if we do that, we can get these values straight away. So 0.05 gives us that 0.0487 it's telling us here. If we go across there, it does show that to a greater number of significant figures, greater precision. And if we go down, we've got 0.25 there, so that's the value that I wrote down. And down to 0.8, again 0.6506666, and so on. Now, the next part of the question asks us to comment on the accuracy of the estimates. Well, we can now go back to learn of 1.05, and it gives us a value what that to really show why that's happening on the graph. So if we look at the graph of y equals ln of 1 plus x, which Desmos can plot for us, and we look at the graph of just the first two terms of the Maclaurin series, y equals x minus a half x squared, you can see that that is a pretty close fit for the graph up to about x is 0.3. So you can see it starting to diverge there. If we add in a third term here, y equals x minus a half x squared plus a third x cubed. So really what we're doing is we're modeling ln of 1 plus x with a cubic graph. There it is. And you can see that that's accurate for a little bit longer, perhaps to 0.5, x equals 0.5. Let's just take that one away. Maybe not quite 0.5, 0.4 perhaps, and minus 0.5, 0.4 over here. If we add in another term, x to the power of 4, it goes back that way again. It's accurate for a little bit further. It's not very much better, is it? But a little bit better. And if we add in the fifth term, again, a little bit better again. So the more terms we have, the better we can model our function. So that was quite a long example. Let's just go back and look at the second example of Maclaurin series over the page. So part A of this says find the first four non-zero terms in the Maclaurin series of sine of x. So what we need to do is we need to start by looking at derivatives of sine of x. So we're going to say let f of x equals sine x. Then f dashed of x, we know how to differentiate sine, is cos x. F double dashed of x is minus sine x. F triple dashed of x is going to be minus cos x, and f, the fourth derivative of x, is going to be sine x again. So f of 0, we know that sine of 0 is 0. F dashed of 0 is 1. F double dashed of 0 is 0 again. F triple dashed of 0 is going to be minus 1. And f fourth derivative of 0 at 0 is 0. And I think you can probably see that these are going to be alternating again. So we're going to get another 1, 0, minus 1, 0, 1, 0, minus 1, 0, and so forth. So using the formula for Maclaurin series, we've now got sine of x is equal to, well, f dashed of 0 is 0, plus f dashed, f of 0 is 0, f dashed of 0 is 1, so plus 1 times x, plus 0 x squared, minus x cubed over 3 factorial, plus 0 x to the power of 4, plus x to the power of 5, 1 times x to the power of 5 over 5 factorial, plus 0 x to the power of 6. So this is the first four non-zero terms, 1, 2, 3 terms, so we need one more. What's it going to be? It's going to be minus x to the power of 7 over 7 factorial, and it goes on like this. So sine of x is equal to x minus x cubed over 3 factorial plus x to the power of 5 over 5 factorial minus x to the power of 7 over 7 factorial. Now we could write out the values of these denominators here, but it is normal to leave this in the form with the factorials in, you know, because it's a bit easier to see the pattern there. Let's just see what those are though. X minus x cubed over 6 plus x to the power of 5 over 120 minus x to the power of 7 over 5040. There we are. And then part B, sine of 10 degrees. Well, this is only going to work if x is in radians, very much like the small angle approximations. This really is a development of our small angle approximation for sine of x. And because we know that differentiation for any calculus that we do, we need to have angles in radians. So we want an approximation for sine of 10 degrees. We need to convert that into radians. So 10 degrees is equivalent to pi over 18 radians. So sine of 10 degrees is approximately equal to, well, we're going to use the first two terms here, as the question says to use the first two terms. So we want x, so in radians, pi over 18 minus pi over 18 cubed over 6. We're going to put that into our calculator and we get 0.173647. So we should give that to a sensible level of accuracy. I'm going to say that's 0.17423 significant figures. So there is a use of excuse me, a use of the general formula for Maclaurin series to derive the Maclaurin series for sine, and then to use that Maclaurin expansion to give an estimate. In the formula book, you will find, as well as the general series for formula for a Maclaurin series, there are specific ones as well. So this is on page 10 of the formula book. It's also repeated on page 18. It's in both the sections for AS Further Maths and for A-Level Further Maths. So here's the formula for the Maclaurin series, and here are specific Maclaurin series for e to the x for ln of 1 plus x. That was the example that we saw just now. For sine of x, which we've also seen, for cosine x, and also for arctan of x. Right, I'm going to leave that there. Thank you for watching. And we'll come back to Maclaurin series again in the next video when we look at compound functions.